Okay, so today we are looking at 11.4, which is about finding limits as x approaches infinity. So as we take a look at these notes, we are on the last page of your packet, which is page number 5, and we are going to talk about when x approaches infinity. We've already said that if y approaches infinity, our limit does not exist. But now we want to know, instead of x approaching -3 or x approaching -9, what if x gets bigger and bigger and bigger? Or subsequently, x could approach negative infinity, x could get smaller and smaller and smaller. We are going to start by doing this from a table, but then tables are kind of tedious, and I don't really want problems to take that long. I'd like to be a little more efficient. So we're going to hopefully discover something that lets us find the limit very quickly. Most students find that 11.4 is pretty straightforward if you can remember a couple little rules. So we're going to look at this first function right here and fill out the table in our packet. So I'm going to pull up my graphing calculator. And I have this already typed into my y equals. So if you want to put in your function, 5x on top and x minus 3 on bottom. And you can look at that graph. You probably see a vertical asymptote. If you think about what we know about this function already, we are going to fill out this table. So I'm going to go to my table setup. Remember, we want this on ask. That means right now my table is blank. And I can say, well, what if x is 10? Or it gets bigger and now x is 100? Or x is 1,000? Or 10,000? Or 100,000? We can look at these y values, and it looks like y is getting closer and closer and closer and closer to 5. If we want to look at our graph, I'm going to change my window a little bit. Maybe I go from -100 to +100. You could go out to 1,000. I just don't want my table, I don't want my graph to take that long to fill. So now my x's are going all the way up to 100. And if you look at this, 1, 2, 3, 4, 5, right here at y equals 5, my curves are really flattening out whether x goes to negative infinity or x goes to positive infinity. So if we come back here, you can fill out your table. You had 7.14, 5.15, 5.015, 5.0015, 5.00002. And we are looking for the limit as our function f of x and goes to infinity as x approaches infinity. And I would say these y values are getting closer and closer to 5. It says, look at your graph. We just did this. As the x's get really, really big, what's happening? Our graph was flattening out at y equals 5. I want you to think about what we would call that on the graph. There's like a vocab word or a special mathematical term that means our graph flattens out at y equals 5. What do we call that? Let's go on to our second function here and see if we can make some more connections. So I'm going to change my equation in my calculator. I'm going to go to my y equals. You can type this in. I already typed some of these in, so I'm going to turn off y1 because now we're going on to our second example. And my window's already changed to 100 and negative 100. So I really am going way out there far. And this time these red curves really flatten out along the x-axis. If you go to your table, it's already pre-filled for you. We already had the same x values, 10 and 100 and 1,000, etc. So now I can see these y values. Take careful note of this e-4. I've had a lot of WebAssign questions about that. If you go down and scroll over them, it gives you the full decimal. So if WebAssign needs more decimal places, you can just highlight that in your calculator and it'll show you more decimal places. But remember, this means times 10 to the -4th. So this decimal here really is 0.0001, or the following would be 0.00001. So those numbers are getting tiny. So if you want to fill those in here, I think writing this out is super important. That scientific notation is not helpful. I feel like if you leave the scientific notation, you don't really see what's happening here. What I want you to see is my decimal got smaller and smaller and smaller. Eventually it's getting so small that I would say my limit is 0. Again, we looked at the graph. Our graph flattened out at y equals, whoops, sorry. Hold on, I just lost my stylus here. It quit working. So our graph flattened out at y, there we go, equals 0. Okay. Third one. And this time we go to our graphing calculator and we go to our y equals, and you can either clear out those previous two or turn them off. So I am turning on my y3. So if you're typing in this new function, you have x cubed plus 1 over x squared minus 5x plus 6. If you go ahead and graph that, I don't really even know what's going on there. That looks super weird to me. So maybe I go back to my standard like zoom 6 and see what's happening. So you can kind of see this wiggling through here. Because I want those x values to get bigger, this time I'm going to zoom out. So I'm going to zoom out. And that lets me see a little more what's happening. I probably have a vertical asymptote here. But then it looks like my function just keeps growing. It gets bigger and bigger and bigger. As x is getting bigger, y is also getting bigger. If you go to your table, again, it pre-fills these numbers for you because we haven't changed our x's. So our x's are still 10 and 100 and 1,000, etc. So it now fills out your y values for our new y3, for our new third example. I can go ahead and fill these in my table. So x gets bigger and bigger and bigger. And so does the y value. If y gets bigger and bigger and bigger, I would say y is approaching infinity. So here I would say my limit does not exist. All right, what's happening to this? Yeah, limit does not exist. Remember, you have 3 reasons for saying your limit does not exist. Your limit does not exist in this case because our function is increasing without bound. Our function is going up to infinity, and we know that we can't do that. We don't have a limit. So what I hope you noticed here so far is that all of these limits were happening at our horizontal asymptote. So if you can remember this one thing, it makes all of this super easy. I don't actually want to fill out a table when I do this. I just want to look at the function they give me. So maybe I can just look at this function and say, where's the horizontal asymptote? That is my limit. So anytime you see this little piece on the bottom, x is approaching infinity, you just need to find the horizontal asymptote. So here's how it works. When I look at examples 1 and 2 right here, I can look at this example and tell you right off the bat the limit is 2/5. Or look at this little example and tell you right off the bat the limit is 0. I did not build a table. I did not look at a graph. I just looked at the equation and very quickly knew what the limit was. If x approaches infinity, I just need to know the horizontal asymptote. We talked about horizontal asymptotes way back in chapter 2, so I just need to remind you how this works. When you're finding a horizontal asymptote, remember you're comparing the degree of the numerator to the degree of the denominator. So let me remind you what that vocab means really quick, and then I'll show you the rules for doing so. If you want to look at the degrees, make sure that your function is in order from largest exponent to smallest. So if we look over here, we have the largest exponent down to the smallest. Sometimes WebAssign will not have those in standard form, so make sure they're in standard form. Then the degree is the exponent. So here my degree is 1, and here my degree is 1. And you compare those degrees. So here's situation number 1. If the degree of the numerator equals the degree of the denominator, then your horizontal asymptote is at y equals the lead coefficient of the first divided by the lead coefficient of the denominator. So notice on number 1 that the lead coefficient was 2, and then the lead coefficient on bottom was 5. So I took this 2 and this 5, 2/5. Anytime that the degrees are equal, that's what you do. Second situation, if we look at number 2 here, in number 2, the degree on my numerator is less than the degree on my denominator. So this degree is 1 and this degree is 2. So my bottom is larger. So then your horizontal asymptote is just at y equals 0. So I could look at this and say, because the denominator is a really big number, then my asymptote's at 0. When we talked about this earlier in class, we thought about a small number divided by something big. So like 10 or 100 or 1,000. As that gets bigger and bigger and bigger, this fraction is tiny, so tiny that you're basically at 0. Third situation is what happened in our third table up above. In our third table up above, the degree of the numerator was greater than the degree of the denominator. And if that's the case, you have a slant asymptote. A slant asymptote means that you have like this slanted line going up, so our function goes up forever. If that's the case, there is no limit. You are increasing without bound, so you would say the limit does not exist. So if you can remember these 3 steps in blue, if you can remember that you just have to find the horizontal asymptote, then you shouldn't have to look at the graph or the table. So I'm just going to look at these one more time for the horizontal asymptote. When I look at number 1, if I don't build the table, if I don't look at the graph, I can see that my degree on top is 1 and my degree on bottom is 1. If your numerator equals your denominator, then your horizontal asymptote is at y equals the lead coefficient on top divided by the lead coefficient on bottom, which is what we had. On number 2, again, we're finding the limit as x approaches infinity. This only works if x is approaching infinity. Because x is approaching infinity, we can find the horizontal asymptote. I compare my degrees. The degree on top is 1, the degree on bottom is 2. So this time the numerator was less than the denominator. I have a little number on top divided by something really large. So my horizontal asymptote is at y equals 0. We saw that in the graph, you can see that in the table. But I hope going forward you don't have to make a table. Just tell me the horizontal asymptote. And then finally, on our third example, your degree on top is really big and your degree on bottom is smaller. If your numerator is greater than your denominator, then you have a slant asymptote. That means your function is going up forever. So your limit does not exist. Your function is increasing without bound. You are going up to infinity. So as you practice this in your homework, I would make sure you are thinking about anytime I'm asked, what's the limit of this function if x is approaching infinity? If x is approaching infinity, then I need to find the horizontal asymptote. And in order to find the horizontal asymptote, I think through these 3 steps right here. Your table should support that, your graph should support that, but my hope would be that you can find that asymptote by just knowing this rule. That's all I have for 11.4.